Hi, and welcome to Module 2, Week 5 already. We've been talking about motion mainly in one dimension, along a straight line, either horizontally or vertically. I'm going to now expand a bit into 2 dimensions and also start talking a little bit about energy and work and power and some of those things. So, talk about motion in 2 dimensions. Projectile motion is a very old, well-established part of physics. It was one of the first things in motion to be studied because it has these military applications. So you can see my very high-tech diagrams there. Obviously, it's applicable in sport as well. How does something move when it's flying? How do we get a path, a trajectory, get a sense of it? It's kind of interesting because anyone who can catch something is doing this calculation in their head. And the calculation actually, particularly once it includes air resistance, involves quite a bit of calculus. But even dogs can catch a ball in the air. So somehow intuitively, we're actually doing very complicated calculations in our heads when we actually catch a ball. When we have 2 forces at right angles to each other, so an example I can think of is if I'm trying to push a train along a track, but I push at right angles to the tracks, I'm not going to be very successful in getting the train to move along the tracks. It's at right angles, it's orthogonal. Or if we have 2 velocities at right angle to each other, when there's 2 vectors at right angles, we can basically ignore one in terms of the other. They're basically independent and irrelevant to each other. So in this case, with a vector, with projectile motion, we can actually divide out the horizontal across the Earth's gravitational field direction from the vertical up and down within the Earth's gravitational field direction and treat those 2 directions differently, separately, which makes it a lot easier to analyze what's actually a very complicated problem. The nature of the beast is that you end up with a parabola shape for most projectile motions if they start from the ground and end at the ground. They don't have to. They can start from up high and go down, or start from low and if you hit a golf ball up onto a hill, something like that. But the kind of classic shape is this parabola shape for a projectile motion. When we actually look at those 2 different vectors, if we divide out the 2 components, we talk about components. And when we talked about vectors, I didn't say much about that in the lecture piece, but I did talk about it in the problem videos. Talked about how you actually take a vector and either take 2 vectors and add them up to make 1, or take 1 vector, as in this case, and divide it out to make 2 pieces. So what we want to do is take the velocity vector. So say I've just kicked a footy. It's going upward at an angle away from me. It's got a velocity, which means it has a magnitude. It's going at a certain number of meters per second, and it has a direction. Its direction is that way. I can divide that out, and I can take the horizontal component of that velocity and the vertical component of that velocity and treat them independently. You can see the equations there on the slide. If you kind of work through, I'll do a explanation video, where I talk about why that's the case. But basically, it's just trig. The velocity itself is the hypotenuse of a right-angled triangle. The vertical is the opposite. So SOHCAHTOA, sine for the opposite and the hypotenuse. And the horizontal is the adjacent, so cos. So the vertical, the Vx, which is the horizontal, is V cos theta of the angle that it's actually put at. And the vertical is Vy is V sine theta. Apologies for that, getting a little bit messed up. So say my initial velocity was 30 meters per second. Now that's a bigger footy kick than I can do, but it's probably, that's a bit over 100 kilometers an hour. So that's probably even more than an AFL player can do. But, okay, so maybe it's a bullet or an arrow or something like that that moves a bit faster again. The initial velocity is 30 meters per second. The angle to the ground, we have to specify where we're doing the angle. Is it to the ground or is it to the vertical? The angle to the ground is 30 degrees. So the horizontal component is 26 meters per second. The vertical component is 15 meters per second if you do the maths on that. If we don't worry about air resistance, and we mostly don't, we mostly go to physics world. We mostly sort of get in that position where that oversimplified world, I talked a little bit about it around Newton's laws. It's like being out in space where there's no air resistance, except that we need gravity for projectile motion, so we can't go out to space. But the air resistance, the maths gets very complicated very quickly. You end up with, I think, second order differential equations quite quickly once you start including air resistance, and it depends whether the ball's spinning and a whole variety of things. But if we ignore the air resistance, then there's no force acting in that horizontal direction. As something travels in the horizontal direction, ignoring air resistance, there's no gravity acting on it, because remember we said that the two directions are independent. The gravity is acting vertically, not horizontally. So the straight line motion just continues in a straight line at constant velocity unless acted upon by an external force. So for projectile motion, it continues going at the same speed horizontally. The horizontal component of this parabola is constant until it crashes into the ground and stops, right? So that element is relatively simple. In the vertical direction, basically you start by going up, or you start wherever you start. You start with whatever vertical direction, vertical velocity you start with. And say it's upward. You've got an upward component of the velocity. It starts out with a velocity in that direction. It starts out with an acceleration opposite to that direction. So the opposite acceleration is a deceleration. It starts off, slows, gets to the top of its motion, and it's stationary at that point. It's got a zero velocity because it's switching from going upward to going downward. And there's a point where its velocity is zero. And then the acceleration due to gravity causes it to accelerate back down again. So we can use the equations of uniformly accelerated motion. Remember from a couple of weeks ago, v equals u plus at, v squared equals u squared plus 2as, s equals ut plus a half at squared. You will have used those a few times. We can use those to calculate because you've got uniformly accelerated motion. The acceleration is always 9.8 on Earth. If we were on the moon, it would be about a sixth of that. So about just under 2 would be the acceleration due to gravity on the Earth. So the thing would do the same kind of behavior, but as you saw with the videos of the astronauts on the moon, when they jumped, their projectile motion was much longer and slower because the acceleration due to gravity was weaker on the moon than it is on Earth. So actually you can get some quite good demos, and there are some videos on YouTube, I believe, that do this, where if you can get a gun exactly horizontal, so that there's no upward component at all, and fire it, and drop a bullet at the same time, at the same place, the bullet will hit the ground just falling at the same time as the bullet that's been fired hits the ground hundreds of meters away. It doesn't seem intuitive. It seems like the one with all the extra speed should stay in the air longer. But in fact, you can do the experiment and it works because the two directions are irrelevant to each other. So in terms of the dropping, that vertical direction, the one that's just dropped stationary and the one that's dropped with a strong horizontal velocity are equivalent to each other. And the time taken for them to get to the ground stays constant in both cases. We'll do one example. I'll go work through another example in an example video and give you some calculation examples to do in a worksheet. But let's just do one example while we're talking. So I've said a car drives off a cliff, and then I added in brackets unoccupied because I didn't want it to be too gruesome as a problem. So our stuntman dives out of the car just as it goes off the cliff and rolls to safety, and the car goes off the cliff. Now it's doing 60 kilometers an hour, which is 16.7 meters per second. Remember, we jumped straight to SI units because it works better that way. The cliff is 20 meters high. So we've got an initial horizontal velocity of 60 kilometers an hour, 16.7 meters per second. We've got zero initial vertical velocity, right? It's traveling horizontally along the ground. So its vertical velocity is zero at the start. The horizontal velocity is going to stay the same, 16.7 for the whole time. So we want to know, okay, it's going to travel at 16.7 continuously from when it goes off the cliff until it hits the ground. So it's going to do a curve like that and hit the ground at the end. We want to know how far from the base, how far from the base of the cliff, this is quite technical, because I'm seeing myself in a mirror. So it's how far from the base of the cliff it's going to land. So we already have a velocity and we want to know a distance. So we need to find a time. So how long is it going to take to actually do its curve and hit the ground? We already have the height. We know that it's 20 meters. So basically what we're trying to do is find out how long will it take something to fall 20 meters from rest? Because that's what's happening in that vertical thing. It's exactly like the dropped bullet. If we find out how long it takes it to fall when it just goes straight down, we also know how long it takes to fall when it goes down in a curve. It's the same thing. So we use the equation s equals ut plus a half at squared. Now in this case, u is 0, so that ut term is also 0, so that just disappears. So we can just say s, the distance, equals a half at squared. We could just plug in everything we've got and rearrange it as we go, like use numbers. So I put 20 equals a half times 9.8 times t squared, and then solve for that. I tend to prefer, although it's something that you can decide what's your personal style, and different students will have different personal styles, I tend to go, let's rearrange it first. So the equation editor has messed with me again. If you rearrange that equation, you get t equals the square root of 2s over a, and that square root sign should be over that whole thing. So it's a fraction, 2s divided by a, and then the whole thing square rooted to get that. So if we substitute in those values and do the calculation, we get t equals 2.02 seconds. So the thing will take 2.02 seconds to hit the ground. And we know that velocity equals distance over time. We can rearrange that to distance equals velocity times time. So we know our velocity is 16.7 meters per second because we already figured that out. We know that the time taken is 2.02 seconds. So it lands about 33.7 meters from the base of the 20-meter high cliff when it comes over at that speed. Now, one of the things I could have done as a teaching thing is get you to predict what you think it might, how far you think it might land. Is it going to just go boom and stop after 5 meters? Is it going to go 100 meters? You know, you could get your students to actually predict what do you predict is going to happen, and then actually do it. And you can do this as an experiment as well. I'm going to roll this marble down this inclined plane across the desk. It's going to fall off the desk and fall to the ground. Put a piece of tape on the ground where you think it's going to hit, and have a Kit Kat bar or something healthier for the person who's closest to where it actually hits, because that's a judgment question, and it's a kind of physics intuition question, which I think is quite helpful. So that's one example. As I say, we'll do a number more examples as we go. But I hope that's helpful, just getting a sense, because the absolute key concept of this projectile motion, remember we've switched from 1 dimension to 2 dimensions. We could do this in 3 dimensions as well. It makes the maths a little bit uglier, but no more complicated. We can divide out the 3 dimensions and it still works quite happily. And the key concept is that dividing out of the dimensions and being able to treat them separately, and knowing that whether there's an acceleration due to gravity or not is the big difference. None horizontally, but some vertically.